Shruti? Shruti, can you hear me?
Yes, sir.
Yes. Start the introduction slides.
Yes, sir, sure. Good morning, everyone. I, Shruti Hyeok, welcome you all to the expert talk organized by IEEE Sensors Council Student Branch Chapter, IIT Indore, on 2D TMD, on 2D magnetic TMDs for spintronics and quantum sensing. Let us begin with the talk. I invite our today's speaker, Dr. Yang. Welcome, sir. Dr. Yang is a professor at Department of Mechanical Engineering, Center of Quantum Science and Engineering, Stevens Institute of Technology, USA. The distinguished lecturer, Dr. Yang, began his tenure as a senior member of engineering staff at NASA's Jet Propulsion Laboratory and led several projects funded by NASA, DARPA, and NRO. At JPL, he managed and monitored several NASA SBIR projects and participated in the review committee for developing NASA's multi-object spectrometer for James Webb Space Telescope. Dr. Young joined Stevens in 2006, securing over 40 federal grants and contracts totaling approximately $11 million, including NSF, AFOSR, NRO, and US Army funding. He is an associate editor at editorial board of scientific reports, Micromachines, and IEEE Sensors Journal. Dr. Young has published over 300 journal and conference papers and has been invited to give over 100 keynote and invited talks for conferences, workshops, and university seminars. He was featured track plenary speaker at ASME IMECE in 2018. He was awarded, among other honors, the Lew Allen Award for Excellence at JPL in 2003, the Award for Research Excellence at Stevens in 2019, and IEEE Technical Achievement Award Advanced Career from IEEE Sensors Council in 2020. The abstract for 2D magnetic TMDs for spintronics and quantum sensing. The presentation will cover 2D TMD with magnetic doping for 2D spintronic devices. While the lack of band gap is a serious limitation for graphene use in electronic devices, reports have shown promising prospects of using TMDs in electronics, optoelectronics, because of their unique properties complementing graphene. In particular, 2D atomic crystals exhibiting magnetic properties provide an ideal platform for exploring new physical phenomena in 2D limit, representing a substantial shift in the ability to control and investigate nanoscale phases. The work demonstrates the 2D dilute magnetic semiconductor at room temperature via in situ synthesis and characterization of Fe-doped TMD monolayers. The substantial doping of Fe and the growth of MOS2 and WS2 monolayer is achieved simultaneously. The presentation shows that Fe incorporates substitutionally into MO and W lattice sites and probes ferromagnetism in FeMOS2 at room temperature. This new class of van der Waals ferromagnetism finds critical application including on-chip magnetic field sources, spintronic memories, spin photovoltaics, and spin thermoelectric. The discussion includes synthesis, doping, and ferromagnetism of 2D TMDs for 2D spintronic devices. I invite Dr. Yang. The floor is open to you. You may now start your presentation. Thank you, sir.
செக்ரட்டரியோட பொசிஷன் என்னன்னு தெரியுமா உங்களுக்கு? அவர் திருச்சி டயசிஸ்ல பெயில் இல்ல, அங்க அவர் அட்மினிஸ்ட்ரேட்டர். அங்க 3 நாள் இங்க நீங்க
Saurabh, please unmute the participant. Professor Young, I would also like to one request. Can we record a meeting for Sensor Council? If you kindly allow.
Yeah, do you see the slide?
Yes, sir. Yes, sir. It is visible for us.
So I'm not quite familiar with, let me see how to, okay, maybe this is better. All right, so this distinguished lecture, this is a part of the IEEE Sensors Council. Okay, let me see. All right, so Sensors Council is an IEEE Technical Council, and members can register as Sensors Council participants, receive newsletters, attend Sensors Council sponsored events, and volunteer. And there are several conference locations, and there are 26 member societies. And for the Sensors Council, there are 38 section chapters and 54 student branch chapters, I guess one of which is yours. There are several conferences that are sponsored by this Sensors Council, and the flagship conference is IEEE Sensors Conference. And this year is going to be held in Vienna, Austria, and there are other conferences here, and IEEE Biosensors and others. And there are even industry-focused events given here. IEEE Sensor Interfaces Meeting and IEEE Sensors in Spotlight. And there are several journals sponsored by the Sensors Council, and the IEEE Sensors Journal is established in 2001, and it has been very popular, and there has been 2.2 million downloads in 2022 alone, and this impact factor of 4.325. And other journals include IEEE Sensors Letters and IEEE Journal of Selected Areas and Sensors, and there are other co-sponsors publications, including the IEEE Journal on Flexible Electronics. And this distinguished lecturer program's objective is to access experts promoting the field of sensors. And currently there are 10 distinguished lecturers with various backgrounds and geolocations. And you already did, and we requested this distinguished lecturer, and that's what we are doing here. All right. And there's a YouTube also channel that is a Sensors Council YouTube channel, and you can also click this if you can. Okay. And there are information regarding the website, Facebook, Twitter, LinkedIn, and YouTube, and also publicity resources. All right. So that's about the Sensors Council. And then now let me share. How do I maybe stop share and then share again, I guess. Let me see, share. Not this one. Can you please mute all the participants except for me, because I hear some background noise there. Someone is talking. Okay, I guess we're okay now. Okay, let me know if you see it.
Yes, sir, it is visible.
Okay, so let's start here. Alrighty, so I'm going to talk about 2D magnetic TMDs, and we grow and we basically synthesize and characterize and elucidate their properties of magnetic materials based on this transition metal dichalcogenides, or we call it TMDs. And so I'm going to talk about mostly on these magnetic TMDs, and then briefly demonstrate their applications into spintronics and quantum sensing applications. Just briefly introducing myself here again is I'm E.H. Yang, Professor of Mechanical Engineering Department, affiliated with the Center for Quantum Science and Engineering at Stevens Institute of Technology, and also distinguished lecturer of the Sensors Council. Okay. So my lab is called Advanced Quantum Materials Lab. We work on 2D material synthesis and nanofabrication. And among these 2D materials, we focus on 2D magnets recently, and there are various applications here, including quantum sensing and memory applications. And in addition to those, we also have projects related to graphene and carbon nanotubes for energy storage and sensing. Can you please mute everyone here except for me? Okay.
Okay, sir. Sorry for the
So
disturbance.
regarding the graphene, so we worked on optically purifying the edges of these graphene structures. So do you see this cursor? Do you see this arrow? No?
Sir, it's visible.
Okay, good. Thank you. So here we have this armchair and zigzag direction of this graphene flake. So this is exfoliated graphene. This is done a long time ago. And basically you use polarized light to selectively burn zigzag edges, leaving these armchair edges. So when you have these armchair edges of graphene nanoribbon, they were supposed to have larger increased bandwidth, which we exactly showed as shown in here. And we also worked on the growth mechanism of graphene that is related to the substrate, which is copper in this case. And we also had these projects, graphene photodetector. We created this graphene and levitate this graphene microribbon here. And then we elucidate these mechanisms, and we learned that the photoelectric effect dominates the dynamics in getting this photocurrent out of these structures. So we grow also carbon nanotubes for supercapacitors application. We also combine these carbon nanotubes with flexible substrates. In this case, we call this half-cured PDMS. So we put these carbon nanotube carpets onto this half-cured PDMS, and then you cure. Then what happens is individual nanotubes roots are tightly bound to this PDMS. They become firmly attached. So what happens is, as you can see in this arrow here, basically you stretch this PDMS substrate, and these carbon nanotube carpets move along this substrate, thereby they don't lose their integrity. Okay, and that is proven on this plot here on the right. It's y-axis is sheet resistance, which doesn't change over the applied strain onto the substrate. So this is a sheet resistance measured through these carbon nanotubes. That means there's no change. That means these carbon nanotubes can be used as electrodes, sensing materials, and others, while substrate is stretched or distorted, and so on and so forth. So this is basically stretchable, materials that can be used as sensors and energy storage and others. So for the sensing applications on the bottom left here, this is a pressure sensor, and the y-axis is resistance. Basically, this pressure sensor works by measuring the change of the resistance. Now, the resistance stays here while we apply this stretching strain. Okay, so you can see that the resistance remains unchanged. And on the right is a glucose sensing. There's a biosensor, and also we see this response current over time. And there are several colors here. So from 0 to 75, these are stretching strain. So when you stretch this substrate, the response current is not affected. Okay, it's not affected by the substrate stretching. So this is a stretchable sensor. Okay, on the right, on the right, and you see this cyclic voltammogram, and which is basically you can characterize the supercapacitor here, and you can see this. So on the right, this shows the y-axis is normalized capacitance, which is not dependent upon the tensor strain that is applied, that is x-axis. Okay, so basically this is a stretchable sensor, and it's independent of stretching, bending, and doing. So that's what we did in regard to the using the carbon nanotubes. And so among these projects, I am going to focus on these 2D magnets. Okay. Okay. So Richard Feynman received the Nobel Prize for Physics in 1959, and he gave this famous lecture at Caltech entitled "There's Plenty of Room at the Bottom." And he said in his lecture, what could we do with layer structures with just right layers? What would the properties of materials be if we could really arrange the atoms the way we want them? I can hardly doubt that when we have some control of the arrangement of things on a small scale, we'll get an enormously greater range of possible properties that substances can have. And this prophetic remark was realized when Gauss and Novoselov first isolated graphene from graphite, resulting in receiving Nobel Prize for Physics in 2010. Graphene is extremely strong, extremely lightweight and flexible, and graphene is electrically and thermally conductive, but at the same time is transparent. It is 1 million times thinner than the diameter of a the single human hair. Therefore, this graphene research makes huge impact in academic research as well as industrial applications. Okay. The problem here is the graphene is a gapless semi-metal. So graphene has a certain limit, okay, in using in the area of electronics optics. For you create graphene transistors, it's difficult to turn off because you don't have the bandgap. On the other hand, transition metal dichalcogenides, there is another different types of these 2D materials, just handle like graphene, and some of these TMD monolayers have direct bandgap. This means that these TMDs can be directly used in electronics and optics, which complement graphene's property of lack of bandgap, right? So this development of these TMD materials opens up the important applications, including surface chemistry, biosensors, electronics, photonics, energy storage, and you name it, including among others, especially the spin manipulation in TMDs using this TMD's broken inversion symmetry has been demonstrated, and this is for electronics that leads to also ferromagnetism, which I'm going to talk about mostly today. There are key challenges facing this TMD research, including the scaling up. Of course, there has been demonstration of wafer scale growth, but how about much larger than wafer scale? Okay, so still this is a question. Control growth for grain boundaries and defects, these are very far from, far from there. And these grain boundaries and defects relates this air stability. Okay, so there are several issues here. And also, how about the control of doping to create alloys of different materials out of these TMDs? So we focus actually this control of doping, and we found that there's something interesting here. And actually, doping is very important in the semiconductor technologies. For example, boron doping makes p-type silicon, and phosphorus doping makes n-type silicon, creating p-n junction transistors, right? It's the same for 2D materials. We are not talking about the p-n junction, but there are a lot of things can be done by doping. Recent studies showed that substitutional doping of 2D TMDs can effectively tune their electrical, optical, magnetic, and catalytic properties. And among these, the properties, we focus on ferromagnetism in 2D materials, okay? So this event of these 2D magnets have been forecasted, since 2018, and there have been several review articles published since 2018. This is a review article published in Nature, the journal Nature, entitled "Magnetism in Two-Dimensional van der Waals Materials," and created a list of potential research topics. And first list was of room temperature ferromagnetic materials. Another article published in the same year by Novoselov, who is a Nobel laureate, and it's about the magnetic 2D materials in heterostructures. And next year, 2019, was a Journal Science, another review article published that is entitled Two-Dimensional Magnetic Crystals and Emergent Heterostructure Devices. So you can see that this is a hot topic. All right. Now, this is a little old one. This is 2006 publication. The Journal Science had this 125th anniversary of this Journal Science, and they created this list of suggested questions that point to the critical knowledge gaps. So basic rules include that the scientists must have a good shot at answering the questions over the next 25 years, or they have to know how to go about answering them. One of those 125 questions listed by the Journal Science was this: is it possible to create magnetic semiconductors that work at room temperature? So that's exactly what we are tackling here. We are adding another layer there. Basically, we add 2D limit. We confine these magnetic semiconductors that work at room temperature in 2D limit. That's exactly what we do. Okay. Okay. Now, for those of you who are not really familiar with this magnetism, what is exactly ferromagnet? What is ferromagnetism? Ferromagnetism is magnetic ordering where the intrinsic magnetic dipole moment on each crystal lattice all align in the same direction under the applied external magnetic field. Okay, can you see it on the top right? So, on the left, there is a random domain orientation, and after magnetization, you have this aligned, okay, magnetic dipole moment here. Now, when the field is applied, so this is after the field is applied, and then you remove what happened, the magnetization does not return right away. That's called the hysteresis. Okay, so from this hysteresis, you can get the magnetic coercivity, and you see how much magnetic field this material will generate, and so on and so forth. Now, if you heat this material above Curie temperature, then the ferromagnetism disappears from the material. But you regain the ferromagnetism upon cooling, which means that you better have high Curie temperature, right, or room temperature or higher. Otherwise, you need to put your material in the refrigerator to get the ferromagnetism there, right? Now, what happens if we confine this ferromagnetism into the limit? These 2D magnetic crystals provide platforms to access the fundamentals of magnetism in reduced dimension. This is because 2D materials themselves largely decouple from the substrate. These 2D materials allow electrical control, and they are mechanically flexible. And these 2D materials can be chemically also functionalized for various applications. So if we engineer and integrate these materials into heterostructures, we can study interplay of distinct physical properties, giving rise to emergent interfacial phenomena. So this research in this ferromagnetism will transform into low power spintronics, on-chip optical communication, and quantum information science into a new level. All right. So first discovery of these 2D materials was done in 2017. So those three materials, I believe, and we have a chromium triiodide on urofilm sulfide. So, and then tungsten diselenide monolayers on urofilm sulfide, and tungsten diselenide monolayers on 10 nanometer chromium triiodide. So basically, this urofilm sulfide is magnetic material, and this tungsten diselenide is non-magnetic material. So what happens is tungsten diselenide becomes a ferromagnet through the magnetic proximity coupling. Okay. So important thing here is TC. So that's the Curie temperature. What's the Curie temperature? 45 K. What about this case? That's a 16.5, and this one, you see, 61 K. Okay. Let's see if I move myself a little bit. I can't. Maybe I move myself up here. All right. The problem here, another problem, in addition to this low Curie temperature, another problem is they are exfoliated materials. So you're looking like this, Scotch tape. Okay. So this gives zero scalability. And these materials were either insulators or conductors, and some of these materials were unstable in air. So now we know what we really need for practical applications. So I would say there were 4 critical factors. One is the air stability to some extent. If your materials put in the ambient condition and they're gone in an hour, that's going to be a problem. So a lot of these materials, researchers have to have this glow box, and you have to manipulate these materials, stack the materials in the glow box, and you have to really package them. You have to really encapsulate the materials with HBN and so on and so forth. Otherwise, the materials will be gone in a matter of hours, days, or weeks. So air stability is important. What about the critical temperature? Or, critical temperature has to be high, or at least at room temperature. Otherwise, the device is not practical, because you basically have to put your device into the refrigerator to be used. Okay. And how about the semiconducting properties? Is always advantageous, because this could be compatible with existing semiconducting devices. Scalability, if you use a Scotch tape method to get these 2D materials or 2D magnets, basically offers zero scalability. You need to provide scalability to some extent, and also uniformity of these materials. Okay. Now the problem here is there was none. There was no report that fulfilled all 4 requirements, all 4 critical factors, until we published our work in 2020. It's entitled Enabling Room Temperature Ferromagnetism in Monolayer Molybdenum Disulfide via in situ iron doping. Okay. So our work was motivated by a couple of theory papers that shows that claims that manganese or iron atoms are substitutionally doped into molybdenum disulfide monolayers, then one will see room temperature ferromagnetism. So that was sort of the claim given by these 2 papers, theory papers. And then more recently, this is 2021, and it's another theory paper that anticipated ferromagnetism here, this yellow part here, and room temperature or close to room temperature ferromagnetism from tungsten disulfide, molybdenum diselenide, tungsten diselenide, if manganese or iron atoms are doped. All right. So we looked into these doping issues because we were interested in these alloys. Okay, making these alloys. We depicted 3 papers here on this doping. So published it in 2016, 2018, and advanced materials and nanoletters on niobium doping on tungsten diselenide monolayers, and rhenium doping and manganese. Especially this manganese doping of molybdenum disulfide monolayer was predicted by theory that will give a room temperature ferromagnetism. Unfortunately, none of these work showed any ferromagnetism. Okay, so what's missing? All right. So so my group started looking into doping iron instead of manganese, niobium, and rhenium, because iron is natural ferromagnetic material, right? Problem here is, unlike these manganese, niobium, rhenium, whose melting points are pretty much low, so it's easier to basically incorporate these into vapor phase during the synthesis of these 2D materials or these TMDs here. In the case of iron, one has to use the iron oxide, whose melting point is close to 1600 degrees C. So how to solve this problem? So you have to use different process here. So we use, instead of using powders outside the heating zone like that, and we basically use evaporate thin films, thereby provide better uniformity in the process, or sublimation or gas flow in this local region, and then put the iron oxide materials there. So a basic mechanism is follows. So basically, it is based on the reaction of transition metal oxide and chalcogen in the vapor phase. So for example, for molybdenum disulfide growth, there will be there's an initial reaction between molybdenum trioxide and sulfur. In our case, this molybdenum trioxide is going to be in the thin film form, right? But conventionally, researchers use these powders. Then what happens is it creates the intermediate volatile suboxide, and then you further sulfuride. Okay, sulfuride is a volatile suboxide. Then these materials are converted into these molybdenum disulfide grains. Then we add these iron oxide particles cast onto the substrate. Basically, we contact this with molybdenum trioxide film deposited substrate. Then we supply carrier gases, argon and hydrogen, as well as the collagen vapor. So basically, that's from the sulfur powder, and then basically you melt them and then vaporize them. So you have to really find the right time or the right temperature, right moment before the furnace is heated at the high temperature for the growth and cooling down. Okay. So that's the result. Typical result, you can get these single crystals of iron doped molybdenum sulfide monolayers, or by tweaking the growth conditions, one can get these continuous large or millimeter scale monolayers. And we examine this AFM scan here to get the thickness. So basically 0.8 nanometer is the typical thickness you get from this monolayer molybdenum sulfide, and optical images also show very clean iron doped triangle here with some sporadic bilayers there. Now, substitutional doping of irons is extremely important. Otherwise, ferromagnetism can come from maybe iron ions somewhere, maybe from some residues, maybe some other substrates, right? Who knows? So it is extremely important that we confirm that this ferromagnetism from this material is exerted from the substitutionally doped iron pairs and through this dipole moment and so on and so forth. So this is scanning transmission electron microscopy, and on the left and right, the images show the contrast-corrected STEM images of this iron doped tungsten disulfide on the left and the iron doped molybdenum disulfide on the right. And at the center, you see the STEM STEM intensity spectra of the selected areas, where iron atoms exhibit approximately 40% lower intensity than molybdenum atoms. So in this way, you can clearly see, confirm the substitutional doping, where the iron atoms replace molybdenum or tungsten atoms. Okay. And then we examined the photoluminescence emission here, and we found very interesting emission here. That is not really a band gap emission, but that's something. So that's figure A. So from figure B, this is integrated PL, and this data on blue is undoped molybdenum sulfide, and then data on red is iron doped molybdenum sulfide per temperature. And this is a standard Arrhenius fit, and basically showing that these are band gap emission, okay? But there's another data set which is related to this iron, okay? Which is not dependent upon the temperature. That was very interesting. So we scrutinized this iron related emission here. Before, we also checked, we basically create control samples to see if one has any related peaks here. Of course, there's none from iron oxide, but you can only see this peak from this iron doped molybdenum sulfide. So that's exciton emission here on the left, about 1.8 or so, and then so undoped, right? The black and red data, but then you can see this iron related emission at 2.28 EV from this iron doped molybdenum sulfide alone. And then DFT calculations, this is by Munier at RPI, and this is dipole transitions clearly show the iron-related emission from this DFT modeling there. And so basically this iron doped emission here. So we further scrutinize this iron emission here. So, but for those of you, especially students here who may not be familiar with this area here, let's see what's the Zeeman splitting and what's the MCD, magnetic circular dichroism effect. So on the left, it shows the band structure, okay? Semiconductor band structure. That's the conduction band on top and the valence band on the bottom, and in between there is a forbidden band. That's band gap. Now, if your material is magnetic semiconductor, it's a semiconductor with a magnetic property, then you will see this conduction band and valence band split. Okay, and that depends on the spin direction. That's the Zeeman splitting. And this spin polarized semiconductor band structure, therefore, also alters the absorption of clockwise or counterclockwise polarized light. So that's called the MCD effect there. So that's what you show. That's exactly what we see here. On the top right, it's the intensity versus energy here. So there is a circular dichroism, basically. Okay, so it's absorption, and the basically you have you shine this light with the left-handed, right-handed, and then the absorption is different. So that's exactly what you see, and you see that at 300K. That means your material is magnetic at the room temperature, and this magnetic circular dichroism also shows this hysteresis loop by sweeping this magnetic field here. Okay, and then you can see this change of these circular dichroism here, right? Negative, the positive, and so on. We have performed several independent measurements to triple confirm this ferromagnetism that is exerted by the substitutionary doped atoms. So ODMR stands for optically detected magnetic resonance spectra, and this is nitrogen Bacon says because basically this defective nanodiamond spun onto the sample. And you have this electron spin, and you have this magnetic field, and basically you get this, you get this Zeeman splitting, okay? And so from the sample with the iron doped molybdenum sulfide, you can see clearly see this increased Zeeman split, okay? As opposed to undoped one with the pseudo magnetic, pseudo field here. So basically you have some splitting here, but then when you have the magnetic field exists in the region, it is an atomic region, okay? Basically you have this increased Zeeman splitting. Another measurement, that is another independent measurement, is SQUI, that is the superconducting quantum interference device measurement here, and you see clear hysteresis curve here that only comes from the ferromagnetic materials all the way up to room temperature, and at the 300K, you still see coercivity, so it hasn't reached the Curie temperature. So from this measurement, we can see, so this is the SQUI result shows this global effect or average effect, okay? You have this average value of magnetic field, and basically, this is magnetic flux, right? And basically, you have this show this coercivity, and basically this means that the Curie temperature is higher than the room temperature. On the other hand, this ODMR result, basically this uses AFM like tips, okay? Basically it gives a local value, which clearly shows that this ferromagnetism comes from these iron doped atoms, not from the global or maybe some iron material somewhere. No, it doesn't work that way. Third independent measurement is basically this was done at Argonne National Lab this time, and it's another SQUID on the A and B, and CD is the same ODMR, the nitrogen vacancy center, but we compare two different materials. One is iron doped molybdenum sulfide, the other one is iron doped tungsten sulfide. The difference here is so you change only by tungsten. However, both of these materials were synthesized in similar way, right? Only a little bit of composition of these transition metals, and temperatures are a little bit different, but overall structures, overall process is identical. That means if you see something from global effect or from residues of iron atom somewhere, ion somewhere, for example, you will have to see the same way. Same thing from this iron doped tungsten sulfide. As you can see, however, at room temperature, you don't see anything, and the wire at room temperature, the iron doped molybdenum sulfide is ferromagnetic, and iron doped tungsten sulfide is paramagnetic. There's no hysteresis, which clearly proves that iron doped molybdenum sulfide is number one, ferromagnetic. Number two, this ferromagnetism comes from the substitutionary doped iron atoms. And another confirmation is from this nitrogen vacancy center, where iron doped tungsten sulfide does not show the Zeeman splitting, increase the Zeeman splitting, while this iron doped molybdenum sulfide shows increased Zeeman splitting, okay, at room temperature. Now, since then, there were several, maybe 3 to 4 papers showing room temperature ferromagnetism from vanadium doped tungsten diselenide. This is vanadium doped tungsten disulfide and the selenide, and another one. So, the competition is fierce. There are several, big groups, get into this area, and they're working on this. Okay, and one of these papers show that because there's several, common question is, what about the doping concentration? How many, what's the percentage of iron atoms, doped iron atoms in these 2D materials? It's not high. In our case, it's 0.5%. There is estimation that we got from XPS result, which I haven't included in this presentation. But interestingly, in this graph on the right, y-axis is phase deviation, x-axis is temperature. So you get some phase deviation. That means you get some ferromagnetic property, and you get better result when you have lower doping concentration. See, 0.1% vanadium, it gives a better result. It gets higher Curie temperature here on the right. Okay. And this is because when you have higher doping concentration, basically you distort your lattice, okay, that are basically dilute, or that are basically, disrupt this magnetic property, and so on and so forth. Okay, now let's move on to demonstration of applications. Okay, so basically how we use these iron doped molybdenum sulfide into device applications, or some sort of different types of applications, okay? Using these iron doped molybdenum sulfide as the base material. And this project is a magnetic proximity coupling. So on the top left, okay, this drawing shows this conceptual schematic. This is cross-sectional schematic here. So we have this gold chromium pillar, so that gives this strain into the material that is basically a stressor that gives that enhances quantum emission. Okay, but let's not go there. That's not the focus of this presentation here. So we have this iron doped molybdenum sulfide. Now on top we put tungsten diselenide, which is not the ferromagnetic material, but it is another TMD. All right, but this tungsten diselenide is the quantum emitter. Okay, so let's go to the right side, and figure A is photoluminescence from tungsten diselenide, and then figure B is focused into 1.6 to 1.75, this area, right? And it at 3.8 K. And you see this sharp spectral peaks here, okay? X0 is neutral to the action, XD is dark to the action, but this one is your quantum emitter, okay? Now, let's go back to the left image here. When you combine this with the iron doped material, basically this iron doped molybdenum sulfide is ferromagnetic, okay, material. And this on the bottom on left, it shows the ferromagnetic property can be induced into non-magnetic material through this magnetic proximity effect, especially when, but this proximity coupling is very thin. You can go maybe a nanometer or sub-nanometer, but luckily tungsten diselenide is what? Okay, point something nanometer. So basically this whole material becomes ferromagnetic, okay? what happens here is then you can manipulate, okay, this delta E, which is basically you have split up this peak into two, okay. As you sweep this magnetic field, basically you can manipulate this quantum emitter using the magnetic field. In a way, it gives optical chirality, okay, into this quantum emitter if we use this iron doped molybdenum sulfide. Now, what if we directly dope irons into tungsten diselenide instead of using this iron doped molybdenum sulfide and then use this magnetic proximity coupling? Then probably we'll get the quantum emitter with the magnetic property with this material alone, right? So that's what we try here. I mean, we haven't done the quantum emitter from here yet, but so on the left, it shows this detailed conditions to get this growth here on the temperature and the supply of selenium and hydrogen and so on and so forth. And on the bottom left, it shows the photoluminescence of undoped and doped tungsten diselenide, showing different generation of neutron exciton, and neutron exciton is enhanced by iron doping, and trion peak quenching happens due to the N-type doping for this doped material here. On the right, it shows optical image as well as SEM images of undoped and doped tungsten diselenide. And we perform this energy dispersive X-ray spectrometry, EDS, and it's a little controversial, and but for now we see these tungsten, selenium, and iron and carbon signatures here. But further confirmation is required to confirm. But I just decided to show anyway. We are working on AFM imaging, AFM mapping. On the right, it is magnetic force microscopy mapping here. And on the right, top right, this is a height sensor image, basically, okay? Just shows the height. On the bottom right, this is a phase image. But it's the same material, same area. But unlike the top right, from the the bottom right, you see some boundaries. And we hope that these are the magnetic domain boundary. If that's the case, we confirm that this is a room temperature ferromagnets, okay? But then recent work, which we have the measurements, but from the collaborator group, so I cannot put them in this slide, and it confirms that the iron doped tungsten diselenide is a very strong ferromagnet. We need further work, and I cannot show it in here publicly. And on the center, and we still need more work, and because our collaborator doing this aberration corrected STEM imaging, and they had some construction in the site, so they couldn't get the very nice image. This is nice enough, but we need further confirmation. So this also shows the quenching here. That means you have iron here, okay? That replaces tungsten, but it's not. It's a little bit. I'm not 100% sure. This may be error, so we'll have to see. But regardless of this STEM result, with that's a vibration scanning microscopy result that I haven't shown here is correct, and we confirm that this iron doped tungsten diselenide is a strong ferromagnet. That's a very exciting result. So let me show maybe three demonstrations, device applications. One is spin photovoltaics. So unlike the photovoltaics that use charges, right? You have these, you shine light, then exciton is created, okay, in the semiconductor. Then you apply voltage to separate electron holes, right, and create depict the photocurrent, right? When you use spin, because this material is ferromagnet, right? Basically, you can add the value. Basically, you have stronger, photocurrent. This is published in Science Advance. Okay, it's a high impact journal, as you know, and it's right next to the journal Science, and that's basically shows they use this 3-layer chromium triiodide here, and basically then show this sharp peak. So we did similar using our material. As you can see, we have similar values here. Of course, there are a lot more things to do to further understand and here, but you can clearly see the enhancement of the forward current under the application of the magnetic field due to the spin current. And I wouldn't say spin current because it's a little controversial. We need further work, but this is magnetocurrent. Okay. So that's that. Another project is magnetic tunnel junction, which is a basic or essential component for magnetic random access memory. And I recently heard that Samsung is developing this magnetic random access memory, or MRAM, using conventional technology. As you can see on the bottom left, it is from this famous Stuart Parkin. They use this, several E-beam epitaxy, molecular beam epitaxy, and sputtering and magnetron, creating this atomically thin, atomically controlled copper iron and manganese oxide and thicker copper iron to create soft and hard magnet. So on the right top, it shows the structure here. So basically, the structure consists of 3 layers. One is free, barrier, and the fixed layer. Okay, so fixed layer is a little harder magnet. Free layer is a soft magnet, so you can flip the magnetic state easier. And the barrier layer basically is a barrier. You can use some dielectric materials there. Okay, that is dielectric on the left here. Dielectric material here is manganese oxide. Another work is published in Nature Materials in 2010. Also shows this very complex structure and shows this magnetic TMR, tunneling magneto resistance. Okay, so how it works is electrons flow through this MTJ, and because this material is magnetic material, basically, it transfers the spin angular momentum between the magnetic layers, and with this spin angular momentum transferred, it changes the state of this free layer, and that will write information there. Okay, so you can do that either by applying the external magnetic field, okay, in different direction, or by a flowing current in different direction. Now, this is a very expensive process, as you can imagine. What if we replace everything by 2D materials? We need CVD system and Raman, AFM, and transfer stage, and okay. So as long as we could potentially match the performance to certain level, and this is going to be much cheaper, faster, easier. So we'll see. We tried. For us, it's not easy. It took us 3 years to get to this level from starting from scratch here. So here we have HBN, we have graphite, the iron doped sulfide, and HBN. Then we have this iron, okay, layer that is a hard magnet, and then we have electrodes. So and then without the tunnel barrier HBN, we show this IV characteristic here that is linear. But then we put this this HBN there, and this is a typical tunneling current. Okay, so tunneling current can be characterized by this Fowler-Nordheim tunneling, and that's exactly what we have per different temperatures. So now we know that we have this tunneling current. Then next is apply magnetic field there. So let's see. Let's look at first. Okay, let's look at the left one here. On the bottom, you see this parallel, anti-parallel, and you have different current level. Okay, and that corresponds to the values from the right. That is y-axis is a tunneling magnetic resistance, which can be controlled by applying this magnetic field, sweeping from negative to positive. So let's look at this cartoon shown on the top right. First, look at the arrow here. Okay, so this magnetic direction, pole direction on this iron doped molybdenum sulfide and this iron, okay, hard magnet is the same. Then you have a high current. High current means a lower resistance. That's here. Please look at this cursor here, and then you increase the magnetic field, basically decrease the negative value there. And then what happens as you increase the value, something flip. What? This soft magnet flips. As it flips, basically you have the higher resistance, therefore tunneling magnetic resistance is shown. Okay? And then you further increase what happens here, and then even hard magnet flips. Therefore, it lowers the tunneling magnetic resistance. Okay, then you go all the way, and then you start going reverse in the magnetic field. You now reduce, okay, decrease the magnetic field, then basically it will flip the soft magnet again, and it will give this higher tunneling magnetic resistance here. All right, so that's what we have, and this is still sort of initial result that we have. We are getting much better data now, but I cannot show that. But then we had issues with this noise. Okay, so we thought that this is maybe because of the instrument, or maybe because of this iron that is rough. Okay, but then we looked at this Nature Materials paper on this tunable spin inject. Basically, it's the same paper. Say it's the same tunneling magnetic resistance, and it's just a fancy wording here. But then we realized that they use a microamps level. Okay, in this case, in our case, it was as you can see, this is a nanoamp level. We have other technical issues that why there's a reason why we had to go to low, but this is not the fundamental issues. We can make it large. So we did that, and basically we decided to copy this work and see if how it works. So basically, it's not exact copy, but kind of similar, because they use FGT and then tungsten disulfide. In our case, we use FGT and then molybdenum disulfide. So it is different but similar. And so we use this structure. Basically, you apply current, okay, like this, and then we measure the voltage here. So that's what we do. That's the Hall sensor basically. So, and then you see this anomalous Hall effect from this, and that's exactly what is shown. And here, this anomalous Hall effect was clearly observed at 4 Kelvin, okay, from this FGT with the coercivity of 0.38 Tesla, which is a little lower of this one published in Nature Materials, because they use the glow box. But in our case, we did it in the just ambient condition, which instantly oxidize the surface of this FGT. So basically, we have FGT oxide and FGT more precisely, but we clearly see this. So now our plan is to replace this one by one. Okay, we don't have the glow box, so replace this material by, say, iron doped molybdenum sulfide, and later on maybe bilayer iron doped molybdenum sulfide and iron doped tungsten sulfide. There are so many combinations when we try. Why do we do that? Because this FGT is not the room temperature material, and you don't show room temperature ferromagnets, but our materials are room temperature material. So in the future, it's possible we can have room temperature computer. It's a spintronics computer based on all 2D materials in the future. That's a little far-fetched, but that's a sure possibility. Okay. Finally, another application is on-chip magnetic field source. On-chip magnetic field. So we work on Aharonov-Bohm effect, in which the oscillations in the resistance of a conducting ring is obtained as a function of an external magnetic flux that pierces the ring. Okay, so here on the bottom right, it shows this schematic here. You send the current, and basically the electrons are split, and then they meet again at the another end here. But then you have this external magnetic field vertically applied, and you will have the oscillations. Okay, because you have this stationary interference of this coherent transported electrons there. So this is what you first see when you measure this at 4K. But these are not exactly Aharonov-Bohm oscillation. You have to find this fine print. Okay, so that's what we did, and that's easier said than done. And there are a lot of interesting work that is involved to get this signal here. Then you perform this Fourier transform there to get these periodic structures that which are signatures of our Aharonov-Bohm oscillations, whose periodicity here depend on the H over E mode and H over 2E mode. That depends on the geometry of this ring and so on. So we need further analysis on these things, but we are very excited that we get this at 4K, because in previous work regarding this graphene-based Aharonov-Bohm, they were characterized in millikelvin level. We show this in 4K, it's quite high temperature. Now, why do we do this? In the future, let me just go back. Oops. sorry, wrong button. Okay, so in the future, we can, so in this add on a bomb here, right? And then we put this top gate and bottom gate and 2D magnets there, and we electronically gate this 2D magnets. You can control even their Curie temperature. You can control their magnetic properties there. So you can manipulate their magnetic property. At the same time, by applying top gate, applying this vertical electric field, you can also, manipulate their Fermi level. Therefore, you can also magnify all these signature. Okay, so right now we do this, but in the future we really have to magnify and enhance the sensitivity dramatically. Why do we do that? Because this magnetic field, this is atom bomb effect that uses magnetic field is mathematically equivalent to the rotation sensing. So basically in the future, this could be used for navigation and gyroscope applications. Okay, but that's far-fetched. Okay, so that's what we have. And this is a very interesting sensing actually applications. Okay, so in summary, we investigate chemical vapor deposition growth of TMDs that includes iron doping of molybdenum disulfide, tungsten disulfide, and tungsten diselenide, and tungsten molybdenum diselenide, as well as their hierarchy structures. And we demonstrated the ferromagnetism in monolayer iron doped molybdenum disulfide, monolayer iron doped tungsten diselenide, as well as other TMDs there, demonstrating the magnetic field strength of 0.5 millitesla from the iron doped molybdenum disulfide. We are exploring magnetic proximity coupling, quantum emitters, and magnetic tunnel junctions, electron interferometers, as well as spin photovoltaic effects right now. So this research unlocks many new opportunities towards this atomically thin magneto-optical, magneto-electrical devices for ultra-complex spintronics, on-chip optical communications, and quantum sensing and energy conversion. Okay, so I want to acknowledge my students here. So this is a recent photo. It's not a complete member, but we have this PhD students and postdoc, and that's me. And I have collaborators here internally and externally. And I also belong to a Center for Quantum Science and Engineering at the Stevens Institute of Technology. And the bottom, this is the logos of the sponsors, the funding agencies. Okay, so with that, I want to show this QR code. If you scan this, basically, you get the form to request the materials for collaboration. So feel free. Okay. All right. So with that, thank you very much.
Thank you, Dr. Young, for your wonderful talk. I hope audience will be able to grasp the topic. So if anyone has any queries, you can post your queries in the chat box, or else you can unmute yourself and ask the question.
Professor Ian,
Yes.
thank you very much for your interesting talk. And my query is related to that, as you have mentioned that air stability is the first concern or major concern related to the 2D TMD material. So what is your opinion about other 2D TMD material such as PDS2? Because in some literatures, it's shown that it is higher thermally stable or air stability compared to other MOS2 and WS2. So what is your opinion about this?
What material was that?
PDS2, palladium disulfide.
Oh, I see. No, I don't know about that, but it depends on the properties. And well, right now, I think still researchers are looking into discovering some interesting phenomena from the materials, and they don't care less about the air stability because you can manipulate everything within the glow box, right? And after fabrication, you encapsulate everything. So, and you measure everything, you publish, then after that, nobody cares. But eventually for industrial applications, this air stability, I think is very, very important. But in some sense, this air stability is intrinsic properties of these materials. So, some materials are less stable, some materials are more stable, and that's not something that you can change. But nevertheless, your material is extremely unstable. Then even with the encapsulation, your material will be become oxidized eventually in a matter of maybe, even with encapsulation, maybe matter of weeks and months. Then I'm not sure how they can be really used in the industrial application in the practical standpoint. So I don't know. I think researchers must take an effort, okay, make an effort to get some this air stable TMDs there, or at least make structures that are stable with the maybe fancy encapsulation or strong encapsulation, whatever you call.
So as you have pointed about the encapsulation, so is there any other way to enhance the air stability other than encapsulation? Because in encapsulation, when we remove the encapsulation, we found the traces or some contamination on the surface. That is the major cause when we
yeah.
for encapsulation.
For optical and some electrical application, you can encapsulate. But if it's a bio application, you want to use those surface property, functionalize your surface, so basically cannot encapsulate. And your material is air is not air stable. It is really reactive in air. Basically, that material cannot be used as biosensor,
Yes,
right?
definitely.
So that's a difficult problem. I published it in, I believe, 2018 in Advanced Materials on how to get your material more stable in air. That is, if you grow, or actually it was grown, if you directly grow your TMDs on graphene, you can basically elongate. You can basically make your lifetime longer because of the surface electric field effect.
Yes, sir.
But yeah, but then the one limitation is you have to put that in graphene or other 2D materials. So in some cases you don't want it. So
Thank you very much, sir. Now I would request to other participants, if you have any queries, you can unmute yourself and ask the queries directly from Professor Yang. You can interact with. So
Yes, there is a question in the chat box. How are the magnetization measurements done?
So magnetization was measured in several different ways. You can do it optically because if you have the magnetic semiconductor, then you will see this magnetic circular dichroism. You will see the Zeeman splitting. That's exactly what we saw from our magnetic measurement. You can use nitrogen vacancy center. You can use squid. There are so many ways to get this local magnetic field as well as average magnetic field that I already explained during my presentation.
There is another question. Is there any theoretical modeling studies carried out?
Theoretical modeling studies on what?
related to the magnetization measurement, is there any theoretical simulation software is available? So we can done the magnetization measurement.
Okay. What was the question? I didn't understand the question.
Question is related to is there any theoretical modeling studies carried out?
There are, yeah, so you can use DFT and, as I explained in my presentation, actually, there were theory papers and regarding what types of the doping, okay, were enable ferromagnetism in what temperature. Okay, so for example, let me see. Let's go back. Let me see different way here. Yeah, here. Do you see the slide?
Yes, sir.
Yes, sir. It is visible.
Oops, wrong one, sorry. Let me see. Yeah, here. So this is a recent work, this table. This is published in 2021. This is a modeling paper, basically. And they predicted the Curie temperature of these TMDs with these dopants, manganese and iron. So as you can see, these modeling results are not really coincide with the experimental results. Hope this answered your question.
Yes, sir.
Yeah. Yeah.
Okay.
Okay. So is there any another question from audience side? Okay. I think there is no question. So it is my privilege to
Shruti,
start.
wait, Shruti.
Okay.
So, any participant, anyone want to ask any question? Okay, go ahead, Shruti. Then.
Okay. I hope my slides are visible.
Yes.
Yes, Shruti. Yes.
Okay. I would like to thank Dr. Young for the time and efforts you took for the presentation. It was such a wonderful and engaging talk.
Thank
I
you.
also thank Professor Shaibal Mukherjee, advisor of IEEE Sensors Council, Student Branch Chapter IIT Indore. Also, special thanks for the to the audience for the patience and for the listening. So we will end our session here. Thank you so much.
Thank you.
Thank you so much, sir.
Thank you. Bye bye.
Bye, sir.
अंकित वो खत्म हो गया मीटिंग है